The initial conditions are just sort of trivial, right? We don't have to do any work there.
Yeah, I would say, I mean, if you have time, I would say just work out what F and G should be based on your initial condition. You know, so kind of follow through the steps that we've done before to identify capital V and capital G from phi and psi. So those should look fairly reminiscent of what you get from D'Alembert's formula. But yeah, I mean, once you plug stuff in, you can just say, yeah, as long as I have F and G that satisfy these two relations, then that'll work. Yeah. Okay. All right. So, yeah, so I know, well, maybe it sounds like some folks have made progress. Are we okay circling back and talking through it now? I see some head nodding. Okay. All right. Does anyone want to say how they started with this problem?
I wrote the Laplacian in terms of R, and then took derivatives and substituted.
Okay, yeah, okay. So you went ahead and you said Laplacian of U is equal to, I mean, you could just straight use the Laplacian in R formula, I guess. Let me make sure I get it right. Yeah, that's right. Or you could equivalently write this as 1 over R, U, RR. Does anyone want to see the details of how to get that? Or, I mean, on the prelim, I think you're just given this formula. So, it's good to know how to derive it from scratch, but yeah. Anybody feel strongly about seeing that formula derived or, okay. I hear no loud assertion that you want to see that derived. Okay. So then, yeah. So Sage, then you got what for the Laplacian of the formula we have? So we have this formula, yeah?
Right. Yeah. So for the derivative with respect to R, I got F prime plus G prime over R minus F plus G over R squared with the appropriate arguments for F and G.
Oh, so that was just the URR part, or?
The UR. Just the first derivative with respect to R.
Right.
Oh, the total thing. I guess it
Yeah.
simplifies down to 1 over
Yeah,
R.
so once you do this, yeah, you don't have to fuss with product rule and everything. So you just end up with 1 over R F prime prime R plus T plus G of R minus T prime prime, sorry. Yeah, but yeah, probably, I mean, I would assume a lot of you all started kind of going the route of computing those things individually, and then, yeah, you have to do all the, product rule, calculus rules and everything. Okay, so that's definitely the way to go. Get yourself an operator in the coordinates that you have your ansatz in. The ansatz is in R and T. You'll make your life way easier if you do that rather than, convert your ansatz to X and then compute in, the Laplacian on X, and then you go back to R lots of opportunities to make mistakes if you do that, okay? All right, so this is the Laplacian of u in that case, in the case where we have this ansatz, right? And then UTT is what? Again, should be relatively straightforward.
Just 1 over r f prime prime plus g prime prime.
Yep, okay. Okay. So I'd imagine some of you all went down a long road that involved, yeah, sort of lots of longer formulations. Yeah, my tip, yeah, again, would just be to, yeah, always see if you can get your operator in terms of the coordinates that you're in. Okay, so we have UTT, right? And if we look back, right, remember we didn't have a C out front here, so we just have Laplacian of u. Indeed, this is our Laplacian of u. So we're good. So we're done with that part. It satisfies the PDE. That's that step, okay? And then for the ICs, as Sage was asking about, okay? If we want to know what U and if we want to know what F and G should be, then we just plug into the initial conditions, right? So we get U of R0 in this case equals phi of R is equal to, well, it's just going to be 1 over R, F of R plus G of R, okay? So we have one formula. This is sort of like the one that we did in recitation last week, right? Now we have a formula that relates F and G to phi. I think we also did this for another quarter plane problem in maybe the recorded lecture. And then U sub t, R of 0, is going to be psi of R. So that's going to be 1 over R. And then we have to differentiate these, right? So we just get F prime at R minus G prime at R because of the minus T that's in the argument of G, okay? So I think it's useful to kind of go through this again, okay? This idea that we've worked out before. So if I want to get back a useful formula from this equation, I need to integrate it, okay? So let me go ahead and multiply it through by R, okay? And then just integrate, you know, from 0 to R, right? So I'm gonna use a different dummy variable in the integrand. So I get the integral of R s psi s ds now is going to be equal to, well, that's just going to be f of R minus g of R minus f of 0 plus g of 0, right? Just using fundamental theorem of calculus, okay? But also I can use this formula too, okay? And in particular, if I plug in just like R, yeah, let me take 2 steps here. So R phi of R is equal to f of 0 minus g of 0. If I plug in R equals 0, then I get 0 is equal to f of 0, sorry, that's a plus g of 0, excuse me. And then I have g of 0 is equal to minus f of 0. Okay. So this I can now write as f of R minus g of R minus 2f of 0. Okay. So again, remember that, you know, this piece here is important, right? Sort of plugging in the boundary, because R, you know, we haven't talked much about it, but R can only be positive, right? Because it's the radius here of our radially defined solution, right? And so r equals 0 is sort of like our boundary in this case. Okay, we have this weird singularity there. So so I can take now this formula and then this formula up here, and I can combine them, right? I can multiply through, by r here, and I get r phi of r equals f of r plus g of r. And, just to go through a calculation like this again, f of r minus g of r here minus 2f of 0, okay? So if I sum these two equations, I can cancel out the g of r here, and I'll get a formula for f of r, okay? So this is the way I back out, capital F in terms of my known initial condition functions. So if I sum them, then I divide by 2, right? Then I get f of r. I'm sort of cleaning things up to 1/2 r phi of r, okay, plus integral from 0 up to r s psi of s, right, plus f of 0, right? And you say, uh-oh, well, that f of 0 is still hanging around, but it's going to cancel out in our final solution, okay? Just like that free constant that we had floating around when we've looked at it before. You can also just express those free constants in terms of your unknown function evaluated at 0, okay? In a similar way, if I take the difference and I divide it by 2 and I rearrange it, then I get g of r is equal to 1/2 r phi of r minus integral from 0 up to r s psi of s ds, okay, minus f of 0, okay? So I'm getting close to having a solution, right? The only thing I need to do now is just to sum these up, right? So remember the form of solution that I said I had was this whole thing divided by r, okay? So I can divide everything through by r, and I'll be done if I sum them together, okay? So I'll do that on the next slide. That's okay. All right. So so then u of rt is equal to 1 over r times f of r plus t plus g of r minus t. And this is equal to then phi of r plus t plus phi of r minus t over just 2, right? Because the r now was canceled out in front, plus 1 over 2r. And I can combine those two integrals, right, by stitching together the limits of integration. And I flip the direction of it here. So if we look back here, right, I can flip the limits of integration just by incorporating this minus sign, and then I just sum the integrals together. And then this one goes from r minus t up to r plus t, right? So I have the integral from r minus t up to r plus t s psi of s ds, okay? And by symmetry, right, since r squared is just equal to the square sums of x1 squared plus x2 squared plus x3 squared, right? Psi of r is equal to psi of minus r, okay? So that initial condition needs to be even symmetric in order to satisfy my assumption, okay? So that's working this out in R3, right? It's a little bit more accessible of a case, I think, than the Euler Poisson-Darboux equation, where we sort of worked it out in general Rn. Maybe you can see how the pieces fit together a little bit more clearly. Okay, questions about that?
Why do you need psi to be even?
So you need to know what psi is for negative values of R, right? And so essentially, just because I can take psi, right, is a function of x, whether or not I take these x1, x2, x3 to all be negative, right? So if you think of the space that you're living in, yeah, maybe it helps to sort of diagram this, right? The idea is that if I have some R defined here from the origin, given by my x1, x2, x3, right? I can't really completely draw this in R3. And the idea is if I was to sort of reflect this ray across to the other side, right, I could think of that as minus R in this case. And because it should live on the same spherical shell here, it should have the same value at that point, right?
That makes sense.
In principle, this would still be R, right? But for the purposes of computing, psi for negative values of R, I can use this assumption. So that's the idea.
Is there a reason that you're mentioning that for psi but not for phi?
Why did I not mention it? Yeah. Oh, it's just because later in the problem we're gonna need that. Oh yeah, I mean it's true for phi as well, right? Right. It's the way that I had the problem set up. So I think that the next step I'm just gonna set phi equal to 0. Okay.
And will we not have the case where the sphere is moved from the origin, like just translated?
Yeah, no, I mean, in this problem, I'm just explicitly looking at spherically symmetric solutions. So we're not doing this whole method of spherical means like I worked out in the lecture, right? But yeah, I mean, if you wanted to sort of build on this and